Hello, PCS 622. So here we go. Let's do a pre-lecture video 11 on the Fourier transform. So this is, in some sense, one of the most important things in the course. It's something that we've been building to throughout the whole semester, and we're finally getting to it now in the later part of the course. Here's the idea. The idea is basically all of the functions that we've applied Fourier series to or Fourier analysis to so far have been periodic functions. And we can only use a Fourier series for a periodic function. And then we had this kind of funny thing where if I had a function which was not periodic, I could just take a chunk of it and then repeat it. That was the periodic extension, right? So I could sort of make it periodic by just looking at a piece of it and then just repeating that piece over and over again. But we always had to have some period, and that was what we had, the period equal to 2L. Now the question is there something I can do to a function which is not periodic at all? So I don't want, like, f of x equals to x squared. I don't want to repeat any of it. I just want to take the whole thing. And it's not periodic. Is there some kind of version of the Fourier series I can do for the non-periodic function? And that's what's called the Fourier transform. That's what we want to get into today. So let's get to it. I'm going to start with a simple kind of conceptual question to illustrate the main idea here. Here's the question. So let's go back to our discussions of waves on strings. So let's say you've got two violins, A and B, which are playing a musical note. And one of them is playing a musical note with a frequency 1000 hertz, and the second one is playing a musical note with a frequency 2000 hertz. Okay. Remember, that's the fundamental frequency of those notes. So go back to lab 2 where we were talking about synthesizing a sound. Let's suppose you're trying to recreate this sound by using a Fourier series. And you want to include frequencies up to 10,000 hertz. Okay. So that's what I'm going to take all the frequencies I need up to 10,000 hertz and try to recreate the sound that the violin is playing. Simple question is, which one of these two reconstructions of this sound will have more terms? The violin A, the violin B, or both the same? Go ahead and take a moment, pause the video, and see if you can come up with a guess for how you might answer this question, or come up with your best vote for the answer to this question. Okay, so hopefully you have paused the video, you've thought about it, and you have an idea for which one of these has more terms in it. Let's work it out. So let's think about these two violins. The fundamental frequency of violin A is 1000 hertz. And that was the n equals to 1 term in the Fourier series, right? And then remember that the other terms come in multiples of this, right? So we have the second harmonic was 2000 hertz. This is the n equals 2 term. And then 3000 hertz is the n equals 3 term. And so on, right? So violin A will have 10 terms in the Fourier series. 1000, 2000, 3000, all the way up to 10,000. So there will be 10 terms in the Fourier series of violin A up to 10,000 hertz. Now how about violin B? The frequency of violin B is 2000 hertz. So what's the second? That's the n equals 1 term for that violin. And then the second one is 4000 hertz. And the third term is, 6,000. They're all multiples of the fundamental frequency, right? This is n equals 2. This is n equals 3. So on. So this one has 5 terms in the Fourier series of violin B up to 10,000 hertz. Okay. Now, what I want you to think about is the number of terms that fit in this range up to 10,000 up to 10,000 hertz. How is it related to the period? So remember here, the period of violin A is 1 over the frequency. And the period of violin B is 1 over the frequency. So which one of these has the longer period? The one with the lower frequency, right? So the smaller frequency here leads to a longer period. And then we saw that the longer period has more terms in the sum. This one has 10 terms in the sum, whereas this one only has 5. And maybe a better way of thinking about it is like, what is the spacing between the frequencies? These frequencies are more closely spaced, right? The spacing between these frequencies is 1,000 hertz, whereas the spacing between these frequencies is 2,000 hertz. That's a general feature. The longer period means that the frequencies which I include in the Fourier series are more closely spaced. Okay. Now the thing which you can start thinking about already is, what if the period is infinitely big, right? So the function is non-periodic. You can start thinking about what is going to happen is the spacing between my frequencies, which I need to include, are going to get really, really small, right? So here the spacing between the frequencies is 1,000 hertz, but if my period gets really, really long, the spacing between the frequencies will get really tiny, okay? And that's where we're going. That's really the sort of essential idea for the Fourier transform. It's that, you know, there's only certain frequencies which can be used in a Fourier series, and those frequencies are multiples of the sort of lowest term. And so there's a spacing between the frequencies which is equal to sort of the lowest frequency. When you make the period long, you're making your fundamental frequency very small, and so the spacing between the frequencies gets really, really tiny. Okay. Basically, another illustration of that. Let's think about a function f of x, which has L equals to pi, and I'm going to write out the complex Fourier series for this function. So I'm going to write C0 plus, and I'm leaving these big spaces for a reason, which you'll see in a second, e to the minus I x plus C2 e to the minus 2ix. This is a Fourier series for a function which has L equal to pi. Okay. So the period of that function is pi over 2. I'm just using the formula for the complex Fourier series. Now let me consider another function, f2 of x. I'm going to write it like this, C0 plus C1 e to the minus ix over 3 plus C2 e to the minus 2ix over 3 plus C3 e to the minus ix plus C4 e to the minus 4ix over 3 plus C5 e to the minus 5ix over 3 plus C6, which is times e to the minus 2ix. This is a function which has L equal to 3 pi. This is a longer period. I wrote these in this funny way to kind of line them up. So you can see that these frequencies here are the same frequency that's included in the Fourier series, and these are the same. But the one f2 has more frequencies in between, right? They're more closely spaced that I'm adding up in the Fourier series. And that's because the period of this function is longer right? L equals to 3 pi here. And so I have, again, more closely spaced frequencies. If I go up to the same value, e to the minus 2ix, I only had 3 terms in the first function, but I've got 6 terms in the second function, or actually more than 6. I've got 7 terms in the second function. So same thing again, right? The longer the period, the more closely spaced are the terms in this Fourier series, and there's sort of more frequencies which fit in a certain range. And if I have an infinitely large period, which means it's not periodic at all, then I'm going to have an infinite number of frequencies in this range. Okay. When we first talked about Fourier series, I mentioned that there's 2 ways to represent a function. Right? There's the usual way, which is kind of in what we call real space. That's just the function as a function of x, and it maybe has some graph, and maybe there's some equation for the function. But if that function is periodic and it has a Fourier series, then I can also represent the function by its ANs and BNs, and we've been drawing these kind of bar graphs, you know. So if I know all of the values of AN and BN, I actually know the function, because the Fourier series is equivalent to the function if I include enough of those ANs and BNs. So we call this real space on the left, function as a function of x, or I can think about sort of in n space, or in like Fourier space. If I know all the coefficients, I also know the function. Now, this was the original representation of the function in terms of trigonometric ANs and BNs. We now have a complex Fourier series, but the idea is basically the same. Rather than AN and BN, I've got the Cn, which is a complex number, which has a real and an imaginary part. So I could do the similar kind of thing for the complex Fourier series. If I knew all the Cn's, it's another representation of the function. Here's a similar kind of graph, but using the Cn's. So on the left, I've got my function in real space. That's f as a function of x. But then if I have these numbers, the imaginary part of Cn and the real part of Cn as a function of n with these bar graphs, so I just know all of those numbers, or in other words, each of those complex numbers Cn, I also know the function. The thing on the left is called the function in real space. The thing on the right is called the spectrum, or the Fourier space representation of the function. Okay. To derive the actual generalization of this to a non-periodic function, which is the Fourier transform, let me represent our function in a slightly different way. I'm going to start with the Fourier series, the complex Fourier series. So f of x is equal to the sum over n equals minus infinity to infinity. These numbers Cn, e to the minus I n pi x over L. Okay. And then we have the reverse, which is Cn was 1 over 2L, integral minus L to L, f of x e to the I n pi x over L. I'm going to start with this one here, and I want to write down a kind of graphical representation of this sum. Okay, so what I'm going to do is try to represent this sum in a picture, and that maybe will help us when we go forward to try to think about non-periodic functions. Okay, so here we go. What I'm graphing here on the right is as a function of n, and I'm putting on this axis Cn times e to the minus I n pi x over L. Okay? So for every value of n, for some function, let's say whatever those Cn's are, I just plot a point, for n equals 1. If I know what C1 is, then I take C1, I multiply by e to the I pi x over L, and I put a dot there. And then I do the same thing for n equals 2, and n equals 3, and n equals 4, etc. Okay? And I would end up with a bunch of these points. Okay, those points, the values of those points are just these things here. Okay. Now, I'm being a little bit sloppy because you know that this is a complex function. So I'm being cavalier, I'm being a bit sloppy. Cn e to the minus I n pi x over L is complex. So if I'm going to graph it, I should really have two graphs. I should have one for the real part and one for the imaginary part. Okay. But the idea is exactly the same. So I would just have a different graph for the imaginary part, and all the steps I'm going to go through are exactly the same. Okay. Now, what I'm going to do here is I'm going to draw in some bars. Okay, so let's draw in some rectangles. Let's say, for example, I add a rectangle here, and then I add a rectangle here, and I add a rectangle here, and here, 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 and so on. Okay. What is the area of each of these rectangles? For example, what's the area of this rectangle? The area of that rectangle is the base times the height. And the base is 1, because you notice the spacing between those guys is always 1. And the height is Cn e to the minus I n pi x over L. Okay? So the area of rectangle, let's call this rectangle 1. And let's call this rectangle 2, and this rectangle 3, so on. What's the area of each of those? It's the base 1 times the height of 1. And the base is 1 unit, because the width of each of those rectangles is 1. And then the height is e to the minus it's C1 e to the minus I pi x over L. Okay? Because that's what I just plotted there. Right? And then I could do the same thing for rectangle 2, for example. Area of rectangle 2 would be equal to 1, the base times C2, e to the minus I pi, times 2 times x over L, right? And so on. What if I add up all of those areas? Sum over all the areas. Minus infinity to infinity, a sub n. This is the total area of all the rectangles. But the rectangles all have a base of 1 and a height of Cn e to the minus I n pi x over L. So this is exactly equal to our Fourier series, right? Sum over n equals minus infinity to infinity. 1 times Cn e to the minus I n pi x over L. Okay. So what I'm interpreting, what I've done here is I haven't done much. I'm just interpreting this sum here as the area of all of those rectangles in that graph. Okay. So another way I can represent that function f of x is by calculating the area of all of the rectangles when I plot this particular graph. Okay. Okay, so this is f of x. Okay, so let's go back to our summation now for f of x. And we said f of x is basically the area of all those rectangles which I drew in that graph there. And it looks like this. N equals minus infinity to infinity, c sub n e to the minus I n pi x over L times delta n. I'm just putting in delta n, which is the space between those points, which we took to be the kind of the width of each of those rectangles. And now I'm going to make a change of variable. So I'm going to change variables to k. Let's call it k sub n is equal to n pi x over L. Sorry, not n pi x over L, just n pi over L. What's the spacing between the k's, delta k, Well, it's pi over L times delta n, right? Let me rewrite this sum now. F of x is equal to the sum over all values of k now. C sub k, so I have to think of c as a function of k now. E to the minus I kn times x. And then for delta n, I'm going to put L over pi times delta k. Okay. Whoops. I'm going to, typical convention here is I'm going to pull out a 2 pi, sum over k, and I have here 2L times c sub k, e to the minus I kn times x times delta k. So that's the same thing as I wrote above. I just pulled out a 2 just because that's what people normally do. And then this is another constant. Ck is a constant, right? And then it's just multiplied by 2L. So I'm going to call this thing, which people normally call it Fk, capital F. This is going to be defined to be Fk, which is 2L times c sub k. Okay. So what do I have there for f of x? F of x is equal to 1 over 2 pi, sum over k, f sub k, which is some constant, e to the minus I kn x times delta k. I really haven't done much. I've just like renamed things, and I've changed from my variable being n, which has a spacing of 1, to my variable k, which has a spacing which depends on the period. So look again, right? What is delta k up here? So delta n is evenly spaced, right? The spacing in n is 1. But if I think about k as being my variable, then the spacing between the k n's is smaller. As L gets bigger, the spacing between the k's gets smaller. This I can still interpret as the area underneath, area of a bunch of rectangles. So let me draw that. I'm just going to draw the same thing that I drew before. So here we go. On the x-axis now is kn. So there's different values of k which I can use. Remember that kn was equal to n pi over L. On the y-axis, I've plotted fk times e to the minus k times x. Put a kn there if you want. And then what is this summation? This summation here is fk e to the minus I kn times x. That's the height of the rectangle. And then delta k is the width of the rectangle. So this summation is equal to 1 over 2 pi times the area of all rectangles below. Okay. But now we can do the amazing last step. The amazing last step is, what happens if L goes to infinity? Take the limit, L going to infinity, which is a non-periodic function, right? If the period of something is infinity, it means it never repeats. What happens? That means that the spacing between my points here goes to 0, right? Delta k goes to 0. And so what is my function, f of x? It's equal to 1 over 2 pi, limit, as delta k goes to 0, this summation. And this should remind you of a Riemann sum in calculus. But as the limit that the width of those rectangles goes to 0, I have the area underneath this curve. The points become really, really closely spaced. K becomes a continuous variable. So K can now be thought of as a continuous variable. not discrete. So k can take any value. And then the sum becomes an integral. And so I have finally f of x is equal to 1 over 2 pi integral over all values of k from minus infinity to infinity, f of k, because now it's a continuous variable, so I'm thinking of my f as not a set of numbers but actually a function for any value of k, e to the minus I k x dk, right? Instead of delta k, when I go to integration, it was dk. This f is what we call the Fourier transform. This is the Fourier transform of f of x. And what is the formula for that? Remember that f sub k was equal to 2L times c sub k, right? And that was integral minus L to L f of x e to the I n pi x over L. Or maybe I'll just write I k n x, just like that, dx. F of k is the limit as L goes to infinity of the discrete version. So that's the integral minus infinity to infinity, f of x. K becomes a discrete, continuous variable, I k x dx. Just like that. Okay. So let me summarize. After all the math, the idea is that I'm generalizing my Fourier series to a non-periodic function. And that means instead of a sum of only adding up certain frequencies, any frequency is possible, and my sum becomes an integral. So I have here f of k is the Fourier transform of f of x, minus infinity to infinity, f of x, e to the I k x dx. This is kind of like the CNs before, right? Except now k can take on any value. This is the Fourier transform of f of x. And then we have a sort of inverse relation, which was up here. This one. It's equal to 1 over 2 pi, integral minus infinity to infinity, f of k, e to the minus I k x dk. Okay. This is what we call the inverse Fourier transform. The inverse Fourier transform of f of k. Okay? So x's position, k is kind of like frequency, right? This here is telling you the representation of the function in frequency space, which frequencies are present. This function is telling you the function in position space, and they're related. You can see these formulas are quite symmetric. There's a few differences to highlight. One is the exponents have opposite signs. In one there's a plus, in one there's a minus. The integration variable is different. So remember, the big F is a function of k, so it can't depend on x. X is an integration variable. The small f is a function of x. It can't depend on k, so k is an integration variable, dummy integration variable. Okay. But otherwise you have this nice symmetry. So this is the Fourier transform. It's a continuous version of the Fourier series applicable to non-periodic functions. And we will do some examples in class to kind of help us get some intuition for what this actually means. I hope you've found this useful, and see you all in class when we try to process this a little bit more.